Welcome to the fourth video in a series of 6 about systems of linear equations in 3 variables. In this video, we'll learn how to solve systems by Cramer's rule. First, a warning. In order to understand this video, you need to know how to calculate the determinant of a 3 by 3 matrix. I have a video called Calculating Determinant by Hand, and it shows how to do this. At this point, you're going to want to either watch that video or pause this one and see if you remember this from another math class. And once you're ready to proceed, let's get back to this one. Here's our first and only example in this video. Suppose we were trying to solve this system of equations for x, y, and z, as we always do. Well, there are many techniques you could use. If you've been watching my videos, you've heard of the substitution technique. You've heard of the addition-elimination technique. And now we're going to learn a third technique developed by a mathematician named Cramer, fittingly called Cramer's rule. It uses 3 by 3 determinants to avoid all of the algebra. It's pretty cool. So here's what you do. The first thing you want to do is be mindful of any coefficients in your original problem that are 1s. Of course, we don't typically write coefficients when they're 1 or -1, so be very mindful of those. Then what you do is you look at all the coefficients of your variables. And in a 3-variable system, you'll have up to 9 coefficients. They're typically on the left side of the equations. And what you do is you make a 3 by 3 determinant using those numbers. Okay, then what you do is you calculate that determinant. Now I calculated this determinant on scratch paper and I got 11. If you're new to calculating 3 by 3 determinants, this is a lot of calculation by hand. Okay, once you're done with all that calculation, we have to do 3 more for a total of 4 determinants to use Cramer's rule. Okay, here's how you set up your next 3 determinants. Notice in the original system of equations, the numbers on the right, these are called the constants. They don't have to be on the right, but in order to use Cramer's rule, they do, and they typically will be. And so what you do with those constants on the right is you put them in the first row of your next determinant. Well, where do we get the rest of the determinant then? You get the rest of the determinant from the original determinant by just pulling down the rows to fill in, the columns. And then, once you've done that, you calculate that determinant. I worked it out on scratch paper. It's a lot of messy work, but I got 44. What do we do for the next determinant? Well, we put that same constant column, but this time we put it in the middle. Where do we get the rest of this determinant? Once again, from the original determinant, the first one we did. Carrying those numbers down gives us that. Once again, I calculated this determinant on scratch paper. Lots of messy work. Not so bad for me. I've had a lot of practice. You may need more practice until Cramer's rule becomes useful. But once I calculated this determinant, I got -11. Now, from the progression here, you probably see a pattern, and you can probably guess what's going to happen on our last determinant, but I'll show you. On the last determinant, you put that same constant column, but you put it in the far right. What do you do for the rest of the determinant? Well, just like before, you pull down the numbers from our original determinant at the top. Recopying those gives me that. Now once again on scratch paper, I calculated that determinant and I got 33. Okay, so we've computed 4 determinants. But wait a minute, aren't we trying to solve this system for x, y, and z? Well, what Cramer figured out is that once you've computed your 4 determinants, you can easily see the answer to the original system. In other words, you can easily see what x, y, and z equal. Here's all you have to do at this point. All you have to do is divide your second, third, and fourth determinant, the ones that have the constant columns in them, by the first or original determinant. And dividing each of these by 11 in this case gives me the answers for x, y, and z. I'll pause while you do those divisions in your head. You should have gotten 4, -1, and 3, of course, and lo and behold, without using any algebra whatsoever, that ordered triple is your answer to this system. In other words, x is 4, y is -1, and z is 3. Pretty cool trick, as long as you're fast at computing a 3 by 3 determinant, which you can be with enough practice. By the way, just to give some formal algebra, these determinants actually have names. You can do the whole process without knowing their names, but there they are. And just to give a formula notation of what we already did, here are the formulas for x, y, and z. If that makes sense to you, it's really just a restatement of what we already did. If the formulas look confusing to you, then disregard them. Everything that you see there on the left and right sides in blue is not necessary for this problem, but I thought I'd give it a more formal look by giving you the actual equations that represent what we did. Pretty cool. That mostly completes the video in terms of problem solving, but I do have some additional comments to make. First of all, watch out for missing variables. Here's an example. If you look at this system of equations, you'll notice that there seem to be some terms missing, but there's no rule in systems of equations that each equation must have an x and a y and a z. You'll notice in the second equation, for example, there's no y term. And in the third equation, you'll notice there's no z term. Whenever this happens, if you're going to be using Cramer's rule, imagine that there are those missing terms with a 0 coefficient. I'll pause while you process that. And once you've done that, you can then set up your original determinant with those zeros as placeholders. And of course, I won't finish this problem, but the point is, once you've set up the first determinant, you could set up the second, third, and fourth determinant using the constant column, which in this case is the 30, the 40, and the 50, and you could proceed from there. So watch out for missing variables. And finally, Cramer's rule only applies for systems of equations that have a single solution. Well, how are we to know then whether we can use it? After all, when we're given a system of equations, they don't tell us whether it has a single solution or no solution or infinitely many solutions. Well, one way you can tell is when you compute that first determinant, if it's not 0, cool fact of matrix algebra, if that first determinant is not 0, which it almost never is, you definitely have a single solution, and then you can proceed to determinants 2, 3, and 4, and Cramer's rule will work. On the other hand, if that very first determinant, the one we call D, is not 0, if it is 0, that means that you either have a system of equations that has no solution, or that you have one that has infinitely many solutions. Either way, not a single solution. If that very first determinant is 0, then you have to determine whether it's no solution or infinitely many solutions by using a different method other than Cramer's rule, such as substitution or the addition elimination method. And that completes the lesson on Cramer's rule.